Nicholas Copernicus led us to the realm of classical relativity. When most of us hear the term relativity, we think Einstein, but relativity was well understood in classical physics. So to understand classical relativity, we need to look at systems in different reference frames, while keeping the origin consistent. What if I'm on a plane and I want to walk to the bathroom? My seat is probably going to be my origin, and the plane itself is going to be my frame of reference. The distance I walk and my velocity will be measured from my seat. First thing I gotta do, wake up the guy next to me who fell asleep before he got the chance to watch Thor on his iPad because he thought that was a very important detail I needed to know before the flight took off. Next, I walk to the bathroom at a steady pace of 1.3 meters per second, which is average human walking speed. Okay, that's cool and all you say, now let's switch reference frames. If we take the Earth as our reference frame, that means we have to take the plane's velocity of about 240 meters per second into account. So let's assume I am walking to the bathroom, and it is towards the front of the plane. So my total velocity measured from the Earth would be my velocity walking to the bathroom plus the velocity of the plane, or 241.3 meters per second. Different reference frames are like observing the same thing from different locations, which are moving at different speeds. There are two types of reference frames. The first is inertial reference frames, which are when our origin is not moving or it is moving with a constant velocity with everything else being measured. Like when my seat on the plane was our origin, because the plane and everything on it is moving with a constant velocity. The second type of reference frame is the non-inertial reference frame. In these reference frames, our origin is accelerating, which means it is not stationary or not moving with a constant velocity. So we cannot simply add two velocities together to get the overall average velocity. An example of this would be trying to walk to the bathroom while the plane is taking off. Even if I am able to walk at a constant speed of 1.3 meters per second relative to my seat while the plane is speeding up, and the flight attendants don't wrestle me to the ground for standing up from my seat during takeoff, my velocity compared to the Earth will be different at each instant because the plane's velocity is changing. We are going to focus on inertial reference frames for the rest of this video. There is a process for going from one inertial reference frame to another. It is called a Galilean Transformation, named after Galileo Galilei. A Galilean transformation is exactly what we did to find my velocity relative to the Earth when I was walking on the plane. We simply add the velocities of both reference frames together, and everything else stays the same. Galilean transformations can be very simple, such as in our plane example, but they can get very complicated as soon as we add the second and third dimensions. We will be going through some more complicated examples in future videos. Cool. This was all stuff that Galileo and Newton figured out. Now let's talk about relativity as it applies to light. Enter our boy James Clerk Maxwell, whose work was very ahead of his time. He calculated the speed of light as 1 over the square root of mu naught epsilon naught, and predicted and provided convincing evidence that light was an electromagnetic wave. Maxwell predicted that light was a wave, and all other waves known at the time traveled through some type of medium. Waves in the ocean travel through water. Sound waves travel through air. A wave propagating down a slinky travels through the solid material of the slinky. Because of this, he predicted there must be some type of medium which light travels through and fills all empty space. That means it would fill the space between molecules in glass, the space between air particles, the vacuum of space, and every other space which matter does not occupy. This would be the medium which allows light to travel. He called this medium the ether, mentioned in the last video. The ether became a very popular and widely accepted concept, but we still did not know for sure if it existed. Combining what we know about relativity and this new theory of how light propagates, we can consider the following experiment. Let's try to measure the time light takes to travel to a mirror and then back again while accounting for the speed the Earth is traveling around the Sun. If the Earth is traveling around the Sun at approximately 30 kilometers per second, a quantity known at the time, then it is moving relative to the non-moving ether, exactly like water waves moving through still water. If we assume Earth is moving in the positive x direction, and we shine a light source at a mirror so that it is also traveling in the positive x direction, then the amount of time light takes to travel to the mirror will be slightly longer than the amount of time it takes to travel back from the mirror. We can see this by doing the simple Galilean transformation from before. The velocity of light minus the velocity of the Earth equals the velocity that light travels to the mirror. And the speed of light plus the speed of Earth equals the velocity the light travels from the mirror after it is reflected. However, this experiment could not be done with enough precision. One persistent scientist devised an experiment with a precision of b squared over c squared, or 1 part in 1 billion. This was the Michelson-Morley experiment, and we will discuss that in the next video. Thanks for watching.